Hello, everyone. I'm excited to tell you about what we've been up to with UCLA SETI over the past 10 years. And I'm thrilled to acknowledge my collaborators, present and past graduate students, Megan Lee, Pavlo Pinchuk, and Adam Greenberg. Our collaborator and a fantastic supporter, Larry Lucina, who is a veteran in the field of SETI, and Ryan Lynch, our friend at the GBT. And I also want to acknowledge the 200 students who've taken the UCLA SETI class over the past 10 years, as they've been integral to this work. So over the past 10 years, we've been using the 100-meter Green Bank telescope to search for narrowband radio signals. And specifically, we're following the great suggestion of Cocconi and Morrison to look in the L band, in the region of frequency space between 1 and 2 gigahertz, where the hydrogen line is at 1.42 gigahertz. This is a phenomenal marker. Hydrogen is the most abundant element in the universe. It has this fundamental transition where there's emission at 1.42 gigahertz. And so we think that's a great search strategy, and that's what we've been doing. Now, how narrowband are we talking about? The WOW signal is about 10,000 hertz wide, and we do not consider that a narrowband signal. In fact, maser emission can be as narrow as 500 to 1,000 hertz. We do not consider that narrowband either. We're specifically looking for signals that are less than 10 hertz wide. And there's a very specific reason for this. And the reason is that nature cannot produce these signals. To concentrate the energy of a signal in such a narrow range of frequencies requires a level of coherence that is just not present in astrophysical settings. And therefore, if we can detect and confirm a narrowband signal emitted from beyond the solar system, we'll have a very strong case that a technological civilization exists with no possibility of a false positive. So that is why we're focusing on these very narrowband signals. Now, when I'm not doing SETI, I'm a planetary scientist and I use radar. And over the past 20 years, I'm responsible for emitting 85 hours of high power, 450 kilowatt monochromatic signals with the 70-meter antenna at Goldstone at 8 gigahertz. Monochromatic signal is extremely narrowband, and those signals have been propagating through interstellar space. And in addition to that, over the past 30 years, my collaborators and I have detected more than 1,000 asteroids. And in every single case, these radar observations start with monochromatic transmissions at 2 or 8 gigahertz from either Arecibo in the past or the Goldstone Solar System radar. And what's important to realize is that there's very negligible spectral broadening by the interplanetary medium for these signals that Vishal described, much less than a hertz. And so these signals are continuing to propagate as narrowband signals out there. This statement about negligible spectral broadening also applies to L-band signals transmitted from a transmitter in the habitable zone of a solar-type star. Almost all of the time, these signals will not be affected by spectral broadening. And so we both emit these signals and we have the capability of detecting these signals. Now, do advanced civilizations still use radar or radio transmissions? That's a good question, and we don't know the answer, but we can certainly not rule it out. Now, the probability of detecting an accidental radar or radio transmission is quite small. And therefore, SETI is most likely to be successful if beacons exist. Now, do advanced civilizations build beacons to advertise their presence? We do not know, but again, we cannot rule it out. And if you're going to advertise your presence, a narrowband signal is a phenomenal way of doing it. It is not a great way to transmit information, but it is an excellent beacon. And so our strategy is to try to detect those beacons. And if we do detect one, we would then immediately expand the search and look for broadband signals in the same vicinity. And those broadband signals could contain information. Now, what is our sensitivity? This chart shows the power required in units of the Arecibo planetary radar power for us to detect a transmitter. And you can see that civilization, an Earth-like civilization with an Arecibo radar, is detectable in our search out to about 125 parsecs, about 500 light years. But of course, an advanced civilizations would probably have no trouble building a transmitter that's a few thousand times Arecibo's equivalent isotropic radiated power. And that means that it opens the volume, the surge volume, to the entire galaxy. Now, that's really significant because compared to the biosignature searches that we're contemplating now, that we are doing now or contemplating in the near future, we have access to a much larger surge volume. So all the biosignature searches that we've talked about now or in the near future are in this little bubble, this little red dot there around the sun. And the little circle represents the 500 light year radius that I've just described, where an Arecibo radar is detectable in our search. And then an advanced civilization with a few thousand Arecibos would be detectable throughout the entire galaxy. So in terms of surge volume, the volume that's accessible to our search for technosignatures is about 1 million times larger than the little bubble where all the biosignature searches are taking place. And in terms of number of accessible targets, our number for technosignature search is about 1 billion times larger than the number of accessible targets to biosignature searches. So over the past 10 years, we've taught a full-length SETI course at UCLA. And this is a fun course in which students learn about astronomy and radio astronomy, and then they design a SETI observing sequence, and they use the Green Bank telescope to observe these sources. We download the data, they learn about Fourier transforms, they plot dynamic spectra, we store the results in databases, so they learn about signal processing, database management, and then they write code to help improve a pipeline. And every year we improve a pipeline as a result of student contributions. And so ultimately we write peer-reviewed papers and we include the students, our co-authors, because they very much deserve it. So what have we done so far? This is a long table, so just focus on this last line here. We've observed so far about 150 primary targets, but as Mike Garrett and his student have demonstrated, that's not the number that really matters. What really matters is how many stars you're capturing in your beam. And the beam of the GBT at 1.42 gigahertz is, 8.4 arc minutes or something like that. So we've observed close to 70,000 stars and planetary systems. And in the process, we've detected more than 100 million candidate technosignatures, narrowband technosignatures. That gives us a fairly high hit rate density, that's the number of signals per unit bandwidth per unit telescope time, of 20. This is a couple of orders of magnitude more than other surveys that use the same telescope, the same receiver, and the same detection threshold. Now we want to quantify the surge volume. And so we are starting with the Drake figure of merit, which is an excellent figure of merit, contains 3 very important parameters to quantify your search. So the first one is B, that's the bandwidth. That's the region of frequency space you're searching, obviously an important metric. Omega is the fraction of the sky that you're covering, another very important metric. And then in the denominator, you have the minimum detectable flux that tells you about the sensitivity of your telescope, also a critical quantity. However, Frank's metric is missing 2 key parameters. So the first one is the drift rate coverage of the search. And I want to illustrate this with an illustration of a dynamic spectrum where time increases down and frequency increases to the right. And you can sample, you can try to detect signals at a variety of frequency drift rates, which correspond to the line of sight acceleration between the transmitter and the emitter. And obviously, that's an important dimension of your search, and it has not been captured in Frank's figure of merit. So we're proposing to add this factor, and we're also proposing to add the pipeline efficiency. So Frank probably assumed that a radio SETI pipeline would be 100% efficient at detecting the kinds of signals that it's designed to detect. But it turns out that's not true. In current radio SETI pipelines, there's at least an order of magnitude difference in the pipeline efficiency. So these two factors we're proposing to add into what we call a modified Drake figure of merit. And we can use the values to compare our search here in blue to historical searches, the search of Horowitz and Sagan, the 5-year ATA search by Harp et al., and then the breakthrough listen searches of Enriquez et al. And Price et al. And you'll notice that our telescope time allocation is a factor of about 40 less than the Price et al. Result, and yet we're within a factor of a few in terms of search volume, and that is because we're covering a larger drift rate range and we have better pipeline efficiency. Now, is the drift rate coverage that we adopted adequate? We search about plus or minus 9 hertz per second, and I'm comparing this to the line of sight accelerations that you get from a variety of systems. And I'm comparing this to the catalog of confirmed exoplanets. There's no guarantee that the transmitter is on an exoplanet, but again, we can't rule that out. It's a reasonable place to start. And so the range of drift rates that we use can accommodate 73% of the confirmed exoplanets out there. Now, if you restrict it to planets that have a semi-major axis larger than 1/10 of an AU, then we capture 100% of the orbital line of sight accelerations. And in terms of spin accelerations, we capture 100% of Earth-sized planets, provided that their spin period is larger than a breakup rate, and 100% of Jupiter-sized planets, provided their period is larger than 11.5 hours. So we're thinking this range is pretty good for the kinds of exoplanet environments out there. Now, we're also interested in quantifying an upper bound on the fraction of stars that have transmitters. And when we tried to do this, we looked at 5 or 6 estimates that were published in the literature, and they were either incorrect or incomplete. And so we decided to write it down. So when you perform a SETI experiment, it's essentially a set of Bernoulli trials with a probability of success P. And that is the product of 3 independent probabilities, 3 numbers between 0 and 1. So the first is the fraction of stars with a transmitter. The second quantity is the pipeline efficiency, a number between 0 and 1. And the third is the transmitter duty cycle, also a number between 0 and 1. So you form that product, and then you can evaluate the probability of obtaining 0 successes when you conduct n observations or n trials at a given confidence level. And it's a simple expression. It's 1 minus p raised to the nth exponent. And you can solve for the fraction of stars that have a transmitter. And this is the solution. In the denominator, you have, again, the pipeline efficiency and the duty cycle. Now, if you assume that the transmitter is always on, duty cycle of 100%, and if you assume that your pipeline efficiency is close to 100%, then this expression at the 95% confidence level reduces to what's known as the rule of 3. And this is the expression that was in the Cyclops report. So we feel pretty confident about our expression. And when we plug in the numbers, this is what we get. And we can focus. So this is the maximal fraction of stars with detectable transmitters in our search. And we find that out to about a kiloparsec, we have at 100% duty cycle, we have something like 7 times 10 to the minus 4 at the most stars with a detectable transmitter. And if we extend that to 20,000 light years, we have fewer than 1% of stars with a detectable transmitter. Now, how do you quantify this pipeline efficiency? And if anybody can do this, anybody who has a radio SETI pipeline can do this. The way you do this is you inject signals, run them through your pipeline, and verify whether your pipeline detected the signals that it's designed to detect, right? So here's our raw dynamic spectra. Here we've injected artificial signals. And in this particular case, we injected 10,000 signals with a uniform distribution of frequencies. What you see here is the notch filter of the GBT. So we don't simulate signals in there because we don't search this frequency range. And then a uniform distribution also in frequency drift rates. And here are the results. Again, as a function of frequency, this is the signal counts. The injected signals are in brown and the recovered signals are in orange. And you can see that by and large, we recover them pretty well. There are two regions of the spectrum where we do less well, and those happen to be regions where global navigation satellites exist, the GPS and GLONASS. So overall recovery through the entire frequency search range is 94%. If we exclude those nasty GPS regions, it's closer to 98 or 99%. Now, we were interested in figuring out what happens when you apply incoherent averaging. So here's a dynamic spectrum again. With UCLA SETI, we use a 3 Hertz resolution, and we keep the full time frequency resolution of the data. Breakthrough Listen has decided to do a time averaging to reduce the data storage requirements that are considerable. And so they average in the time dimension by a factor of 51. That's known as incoherent averaging. Now, that saves storage space, but it has dramatic consequences in terms of detectability because you're spreading the signal over Doppler bins. And so when we do the same exercise with the same 10,000 injections and apply a coherent averaging by a factor of 51, and in addition, we use the Turbo SETI pipeline, we find that out of the 10,000 signals, we only recover 570. So that's a much smaller pipeline efficiency than our current pipeline. Now, it's not entirely fair because the Breakthrough Listen survey did not search plus or minus 9 Hertz per second. However, the distribution of drift rates is uniform, and so we can easily scale from the 8.9 of our search to the plus or minus 2 Hertz per second that Enriquez et al. Searched, and that gives a pipeline efficiency of 25%, or the 4 Hertz per second that Price et al. Searched, and that gives us a pipeline efficiency of 12.5%. Let me skip that. Here I want to show our signals as a function of frequency, and I have this in linear space and then in log space. This is a sample of 4 years of data where we detected something like 40 million signals, and our pipeline automatically classified 99.4% of these signals as a terrestrial radio frequency interference. Now that's good, but that still leaves a large number of signals to examine. And
2 minutes.
Thank you. The most promising of these signals, in my opinion, are outside these RFI regions, and we take a very close look at all these signals. So the upshot is that we've had many interesting signals. However, we're proud to say that we have had no need, we're a little bit saddened to say, but we're also proud to say that we've had no need for reobservation at the telescope after 10 years of observations and 100 million detections. Every single one of them we've been able to attribute to a human origin. Now, we want to improve that automatic detection of RFI, and we've used an AI tool developed by Paul Pinchuk to do this. And this is a convolutional neural network that managed to reduce the visual confirmation burden by an order of magnitude. And here is Paul's network. We're now in the process of building another AI tool, and I encourage you to look at Megan Lee's poster. And the goal here is to automatically recognize prevalent forms of RFI and excise them from our data. And to build the training set that Megan is using to train this AI tool, we developed a citizen science project, and we're very excited that about 40,000 people have helped us classify signal, build that training set that Megan is now using in her research. I want to acknowledge our funders. We would not be able to do this work without the generous support of funders. Thank you so much. We did have a 3-year grant from the NASA Exoplanet Research Program, one of those very few NASA grants dedicated to SETI. And regrettably, immediately after awarding it, they changed the scope of the XRP program, making the renewal essentially impossible. So again, we very much rely on philanthropic support. I'm going to leave my conclusions here. The highlights is we've observed 70,000 systems so far, detected 100 million candidate signals, and we've had no detections and no need for reobservations. Our pipeline is fairly efficient at 94 to 99%. That's not the case when you do incoherent averaging. The efficiency drops to much lower levels. And then we find upper bounds on transmitter prevalence of 7 times 10 to the minus 4 at the 95% confidence level out to 1 kiloparsecs. We know that several published estimates need revisions because they do not include the pipeline efficiency in their calculations. And then finally, we've enjoyed teaching the SETI course at UCLA, where we've involved about 200 UCLA students in SETI. Thank you so much.